last problem example. This is number 53 from the text. And number 53 has a car being driven by the reader of the problem. One of my favorite things, right? It's left to the reader. Initial velocity here, 16 meters per second. And, well, someone in another car decides to try to back out here while you're moving down the road. Yeah, it's kind of dicey. Okay, so they start backing out. And your car has the capability to decelerate or accelerate in a negative fashion at 3.2 meter per second squared. Now, why did I decide to put a negative sign there? Yeah, we're slowing down, right? Which means our speed is going to decrease by what? By 3.2 meters per second for every second of motion from my original 16. So in the first second, we'll be going, what, 12.8 meters per second. And then second will be 9.6 meters per second. So every second of motion, we decrease our velocity by that quantity. Part A, well, okay, so we're going to assume we stop in time. That's always good. So, we stop just in time. So our final velocity there is what? It's 0. Good. So part A asks us to find, okay, what is the time to stop? How long does it take to stop? Part B says, if your time in stopping was half, so if you're at half the time required to stop from part A, what is your current speed? What is that final velocity? Is it equal to 8 meter per second? Is it greater than 8 meter per second? Is it less than 8 meter per second? It'll be one of them, right? Part B says, okay, calculate it. And then part C gives you a little example of reaction time. So it says that if the displacement is 55 meters, okay, how much time do you have to react? In other words, how long can you wait before you press the brake? Well, I'm not going to do that in real life. I'm not going to put that to the test, but they're saying we could calculate that. Okay, so knowns and unknowns. Remember that in part C, the 55 meters is if that happens to be the time, the distance that you travel in stopping. Not necessarily will be, but if that is how far away you are from that car that's coming out of its driveway, then how long can you wait? So the first time we want to find out the time to stop. So knowns and unknowns. Initial velocity is 0. The initial velocity is non-zero. It's 16 meters per second. Our final velocity is 0. Our acceleration of our car is negative 3.2. We don't know the time, and we don't know the displacement. Okay, so we start thinking, okay, do we need one of the equations of motion? Well, not really. We can get away with that generic equation for acceleration. If you want to call it an equation of motion, then I suppose, yeah, you use an equation of motion. But we can solve it from Bf is equal to Vi plus A delta T. Solve for T. Delta T is equal to Vf minus Vi all over A, which is 0 minus 16 meter per second over negative 3.2 meter per second squared. What's the sign of our answer going to be? Will it be positive or negative? You know the answer to that one. Yeah, it's got to be positive because time can't be negative, can it? Well, fortunately, yeah, 5 seconds. That's one way to know you're right. So it says, all right, if you have half that amount of time, what's your speed going to be? Okay, so That means that the time in part B is going to be 2.5 seconds. Let's think about that for a second. Why don't you check your neighbor? What is that velocity going to be after 2.5 seconds? Half of the time from part A. So it can be equal to 8, greater than 8, less than 8. And why? Locked in your vote yet? All right, well, let's see if you were right. We want to find the velocity after 2.5 seconds. So back to that same equation. Vf is equal to Vi plus A delta t. That's 16 plus, check it, negative 3.2 times 2.5 seconds. What does that give you? Well, that gives you 8, doesn't it? Were you right? Why were you right? Ooh, perhaps you remember that velocity changes at a constant rate if you have constant acceleration. Ah, yes. So it would be, if it's half of the amount of time at constant acceleration, the velocity is going to be half of what it was to begin with. Yes, unlike distance or displacement, displacement is a function of the square of the time, yes? And so now that graph is going to look a lot differently than a velocity time graph. So our position time graph would look like what? Starts out steep and gets shallow, doesn't it, as the speed drops. Our velocity as a function of time graph is going to be linear. So if it's linear, then it's going to be a consistent rate. Okay, part C. If the displacement is 55 meters, how much time do you have to react? Well, what this question begs us to do is actually to find out how far we're going to go in 5 seconds. So let's try it out. What can we do here? Which one of our 4? We want displacement as a function of initial velocity, final velocity, and acceleration. Suppose we can use time. We should do time maybe. Well, let's see. Could we do that one? We should be able to do that one, right? Can we do that one? We should be able to do that one too. We have the initial and final velocity, we have the time, we have the acceleration, we have the initial velocity, we have the time. I'm going to go with the third one just to mix it up a little bit. Why don't you try the second one? See if we get the same answer. So my delta x being equal to Vi delta t plus 1/2 A delta t squared being equal to 16 meter per second times 5 seconds plus 1/2. Watch that sign. Yeah. Otherwise it's going to go further than it should. Negative 3.2 meters second squared times 5 seconds all squared. Okay. So what do you get? $80 meters minus 40 meters. Isn't that interesting? At constant speed, we go 80. Because it's accelerated motion, we're going to go half that distance, aren't we? 40 meters. So that's how far you go in 5 seconds. Is that how far it is to the driveway? No. It's 55. We have 55 meters to go. So that means that we can go 15 meters of distance before we hit the brakes. Now, how far do you think that's going to be? How much time do you think we're going to have? We're going to have 2 seconds? We're going to have 1 second? Or less than 1 second? You know, where's that going to be? Is it going to be between here and here, here and here, or less than? Make a guess. Okay. Now, thinking about this a little bit more, remember that if we're going to wait a certain amount of time before we hit the brakes, our speed is going to be constant, isn't it? Now that we haven't hit the brakes yet, so that speed is still going to be 16. Now we're moving at constant speed. If we're moving at constant speed, no acceleration, then we can go back to our equation for simple motion, where we take the velocity times the time. Distance equals rate times time. What's the delta x? That's the difference between the two displacements. So we have 55, we've gone 40. So the difference between those two is how much distance we're going to travel at that rate of 16 meters per second, which leaves us delta time. So now we can take our 55 minus 40, which should be 15. Divide that by 16, you get 0.94 seconds. So that's the amount of time that one would have to wait before applying the brakes and yet still stop in time, assuming everything is constant. So this might be a little reminder, from driver's training. Remember? Didn't you do the 3 or 4 second rule? The distance between cars? Some people did car lengths. In any event, there's some examples. I hope those are helpful.